July 23, 2010. Royal Canadian Air Force pilot Brian Bess was flying his CF-18 Hornet during a rehearsal for an upcoming air show. He began with a gear-down roll takeoff to warm up the crowd. Next, he initiated a low-speed pass, preparing for a high-angle, slow flyby. This maneuver requires the pilot to pitch the nose up sharply, around 30 degrees. At that point, the aircraft relies on engine thrust and wing lift to maintain controlled flight at around 200 km/h. At air shows, this is often the most spectacular moment. It leaves a lasting impression on spectators. But unfortunately, just as Brian entered the high-angle, low-speed flight phase, the CF-18's right engine suddenly failed. The aircraft veered uncontrollably to the right. With only 60 meters of altitude, in a split-second decision, Brian had no choice but to eject. Less than a second later, his CF-18 slammed into the ground and exploded into a fireball. Fortunately, the ejection seat saved his life. Incidents like this are not uncommon. For example, in 2022, AS F-35B experienced a failure during vertical landing. The pilot had to eject to survive. As of August this year, Martin Baker, a leading ejection seat manufacturer, has saved the lives of 7,727 aircrew members. The importance of ejection seats is beyond question. However, this now essential, life-saving device for fighter pilots had a much different beginning when first invented. Its origin story is full of fascinating developments. Welcome to Chris's Military Base. This is episode 3 of our Military Knowledge series. Today, we'll explore how ejection seats save pilots' lives. From the moment the airplane was invented, saving the pilot's life became a challenge for engineers. In the early days of biplanes, if an aircraft malfunctioned, the pilot could simply climb out of the cockpit and jump off the side. Aircraft were slow and simple back then, so bailing out wasn't difficult. But as aviation technology advanced, aircraft speeds increased dramatically. By World War II, frontline fighter aircraft routinely exceeded 500 kilometers per hour. At those speeds, escaping the cockpit was nearly impossible. Even if you jumped clear, your survival chances were slim. There was a high risk of hitting the tailplane, especially on aircraft like the Dornier Do-335, which had a rear-mounted propeller. One mistake, and the pilot could be shredded instantly. Faced with this challenge, Germany began pioneering ejection seat development. The goal was to forcibly eject the pilot upward, avoiding the tail assembly altogether. The first major challenge for designers was how to provide enough power for ejection. The initial solution was spring-powered seats, relying on stored elastic energy to propel the pilot out. But this method had serious limitations. First, the energy output from springs was not enough to launch the pilot to a safe altitude. Worse, before ejection, the pilot had to manually compress the springs and open the canopy. In an emergency, there was simply no time. The spring-powered design was soon abandoned. It was replaced by compressed air systems. Compared to springs, compressed air could provide stronger and more reliable thrust. It was also simpler to operate. The Germans adopted this solution. Throughout World War II, German ejection seats saved the lives of around 60 pilots. Still, compressed air wasn't a perfect answer. It required many extra mechanical components, like air tanks and valves. The design lacked simplicity and still had room for improvement. After World War II, the British took the lead. The Martin Baker Company began developing their own ejection seat. Unlike the German design philosophy, they decided to use more powerful propulsion materials. Their ejection seats were powered by explosives. The firing mechanism was mounted on the seat's back, packed with smokeless gunpowder. When the pilot pulled the handle, the charge was ignited. propelling the seat at high speed. In principle, it worked like a bullet fired from a gun barrel. With the concept in place, it was time for testing. But testing ejection seats was no easy job. The sudden acceleration compressed the spine. If posture was correct, the force could be absorbed evenly. But even a slight misalignment could result in dislocation or spinal fracture. So testing required immense courage. A factory worker named Bernard Lynch volunteered for the role. He pushed his body to the limit again and again. His bravery wasn't just on the ground. On July 24, 1946, he participated in Martin Baker's first live test. At 480 km/h, he successfully ejected from a moving aircraft. And that wasn't the only time. He ejected 30 times in total. A true British Superman. Thanks to his efforts, Martin Baker developed the world's first practical ejection seat. And soon, it was put to use. In May 1949, in the UK, during a test flight of the experimental flying wing off 52, the aircraft began to shake uncontrollably, as if it was about to break apart midair. The pilot made a swift decision to eject and survived. Although this was progress, the early ejection seats were still far too complicated. Pilots had to manually separate the seat and deploy the parachute. This entire process took at least 10 seconds. If the aircraft was too low, or the pilot lost consciousness during ejection, survival was almost impossible. Clearly, there was still major room for improvement. As the aerospace industry advanced, aircraft speeds entered a new era. Supersonic flight became the standard. With that, tail structures became larger and taller. Once again, engineers faced the same dilemma as in World War II: how to safely eject pilots from increasingly faster aircraft without hitting the tail fin. The simplest solution? Add more explosives to the seat. Increase the thrust. But current ejection seats already produce acceleration near the human limit. Any faster would be deadly. At this point, some engineers came up with a wild idea. If ejecting upward hits the tail, why not eject downward? Enter the U.S. Air Force F-104 Starfighter. It was equipped with a downward-firing ejection seat. But this design had fatal flaws. To eject at low altitude, the pilot had to roll the aircraft and point the belly upward to escape safely. In a real emergency, that was a death sentence. This downward ejection seat cost the lives of over 20 US pilots. Without a doubt, this concept was abandoned. To ensure safe ejection without injury, engineers went back to the drawing board in search of new propulsion solutions. The goal was to maximize altitude and control without compromising pilot safety. After extensive research, engineers set their sights on rocket boosters. Compared to explosives, rockets offered several advantages. First, they provided greater thrust, capable of launching heavier seats more rapidly. Second, in explosive-based seats, charges are installed at the seat-o-cockpit joint, producing peak acceleration in an instant. After that, the seat relies solely on inertia. Once ejected, trajectory control is lost. But rocket boosters can be mounted behind the seat. Their burn time lasts 2 to 3 seconds during ejection. This allows for dynamic adjustment of the seat's attitude and flight path mid-ejection. The acceleration is smoother and sustained, placing less strain on the pilot's spine. With rocket booster assistance, ejection becomes less restrictive. It enables zero altitude, zero speed safe ejection. In modern ejection seats, rocket boosters are the definitive solution. Any system requiring short bursts of acceleration almost certainly uses rocket assist. For example, the US retrofitted the F-100 with rocket boosters to enable short takeoff distances. A launch rail was used for vertical lift. Even a heavy C-130 transport plane was once outfitted with rocket pods for brute force takeoff, allowing propeller aircraft to launch in short distances. It's not just on aircraft. The Soviets, seeking to improve tank mobility on muddy terrain, even mounted rocket boosters on tanks. However, this design, while effective for freeing stuck tanks, severely reduced survivability. If a booster was hit, game over. As a result, it remained a prototype only, though never realized in practice. The concept lives on in video games. In World of Tanks, the Chinese series features rocket boosters mounted on the rear sides of the hull. When activated, the boosters deliver a power-to-weight ratio of up to 30 ton, accelerating a 60-ton tank to nearly 60 km/h in seconds. That's true rocket-powered mobility. August 20th, World of Tanks China server anniversary event is live. Log in to participate in the event for a chance to earn generous rewards. One highlight is the BZ-75 rocket-assisted tank, designed with visual inspiration from Guanyu, a mighty warrior on the battlefield. In combat, the BZ-75 carries 18 rocket boosters on its rear. Across open plains, its mobility rivals that of a medium tank, and the new Guanyu skin? Absolutely stunning. It looked insanely cool, like a real-life transformation, with the tank becoming Guan, yes, Red Warhorse. If you want to pilot a tank in battle, equipped with rocket boosters and Guanyu spirit, and charge the battlefield yourself, landing that one-shot kill with your turret, then World of Tanks is your best bet. Download the China version now and experience thrilling armored battles. Now, back to ejection seats. Once rocket boosters were adopted as the new power source, many challenges still remained. Ejecting from supersonic aircraft posed a major problem. Extreme airspeed caused violent deceleration forces on the pilot. After all, no one had ever tested ejection at supersonic speed, which brings us to another key figure in ejection seat development. America's own Superman, John Stapp. Stapp was fascinated by how rapid deceleration impacts the human body. So he built a rocket-powered sled for live testing. The rocket boosters produced 18 tons of thrust, accelerating the sled to 960 km/h on rails. It would then slam into a water trough, coming to a complete stop in under 15 seconds. It was sheer madness. Stapp endured deceleration forces of 20 G. After one test, his ribs were broken, and all the blood vessels in his eyes ruptured. But Stapp wasn't done. He pushed for more. In his final test, he pushed his body to the limit, experiencing an astonishing 40 G of deceleration, twice the previously known threshold. He survived. His tests proved definitively that ejection at supersonic speeds was survivable. In 1955, during an F-100 supersonic test flight, the aircraft lost control at around 2 kilometers altitude. It nosedived rapidly, reaching speeds of 1,250 km/h. The pilot had to eject, enduring nearly 40 G of deceleration. Though his body was swollen, he ultimately survived. With the supersonic challenge overcome, ejection seat technology entered a new era, and in the years that followed, some pretty interesting designs emerged. In 1956, the U.S. Air Force unveiled its new supersonic bomber, the B-58 Hustler. It could reach Mach 2, with a maximum ceiling of 19,000 meters. At those conditions, standard ejection was impossible. Engineers had to create a new ejection system tailored for the B-58. Their solution? Each crew member would be fully enclosed in a capsule. When the ejection sequence is triggered, a mechanical system pulls the pilot's legs into the seat. Then the entire ejection capsule seals around the pilot. The capsule becomes pressurized and supplies the pilot with oxygen. The whole system seems very well engineered, but the risk of live ejection tests was too high. It wasn't realistic to risk a pilot So to verify whether the capsule design worked, the U.S. Air Force used a small black bear. It was launched from over 10,000 meters. In a supersonic ejection test, the result success. The bear survived, although judging by its tongue, it was probably terrified. All in all, the capsule ejection system was a success. During the Cold War, the B-58 completed 9 successful ejections, saving more than a dozen pilot lives. Another unique ejection system appeared on the F-111. Unlike most aircraft, the F-111 didn't eject seats. It ejected the entire cockpit module, like a mini space capsule. When the pilot pulled the handle, the seatbelts tightened automatically to keep the pilot's spine upright. An emergency oxygen system engaged, providing 10 minutes of breathable air. All external cockpit cables and lines were severed with explosive charges. Then the rocket engine beneath the pod ignited. The increased pressure triggered explosive bolts at the fuselage joint, fully detaching the cockpit module. The system had 2 rocket nozzles. Sensors adjusted thrust based on ejection speed. At 550 km/h ejection velocity, the main nozzle produced 4 tons of thrust, and the secondary nozzle 32 tons. The coordinated thrust kept the module's flight path level. Compared to ejection seats, this system was much more stable and far more comfortable for the crew. During the Vietnam War, the F-111's ejection capsule saved numerous pilot lives. Although ejecting from supersonic aircraft is technically challenging, in reality, it rarely happens. Most ejections occur at lower speeds, such as during takeoff or landing. The next issue to solve was, when pilots eject, they've usually lost control of the aircraft. At that point, the aircraft could be in any attitude. Ejection seats would spin uncontrollably in such conditions. If not corrected in time, the parachute couldn't deploy properly. A delay of even 1 second could mean life or death. Let's return to the incident from the beginning. The CF-18 lost control at just 60 meters altitude. It veered sharply to the right. When the pilot ejected, you can see his body was almost parallel to the ground. Had the seat continued at that angle, 60 meters wouldn't have been enough for parachute deployment. But at that moment, you can see the seat's rocket nozzle slightly adjusted its angle. In a split second, it brought the pilot to an upright position. The parachute deployed rapidly afterward. Less than a second later, the F-18 slammed into the ground. In this incident, the ejection seat performed flawlessly at every stage. Every second truly counted, even the slightest error, and the pilot would have had to say goodbye to the world. After 80 years of development, today's ejection seats are incredibly intelligent. Various sensors and chips are embedded throughout the seat. The pilot just needs to pull the handle, and the seat handles the rest. It automatically adjusts posture, separates the pilot, and deploys the parachute. The deployment speed of the parachute, which used to take 30 seconds manually in 1949, has been reduced to under 3 seconds today on the U.S. Navy's F-35. Ejection doesn't even require pilot input. When the onboard computer detects an unrecoverable emergency, it automatically initiates ejection. This minimizes ejection time to the fullest. And this likely isn't the final form of ejection seats. With continued advancement in aerospace technology, more innovative approaches will emerge. If you're interested in the F-111 and its unique escape capsule, feel free to check out our dedicated video on the F-111. It's another Cold War-era high-tech marvel. Okay, that wraps up today's video. If you enjoyed it, don't forget to like, comment, and subscribe. Got something else you want to see? Tell me in the comments. Also, don't forget World of Tanks anniversary event on August 20th. Tons of rewards await new and returning players.